We are going to consider the partial derivatives and then just develop the idea of a directional derivative for this given function 2 plus x square plus 4y square at the point 2, 1. So for partial derivatives, let's just go ahead and follow a mechanical procedure first. So df dx, as you can see, is 2x here. So if we write this partial derivative at, say, or rather at the point 2, 1, how much that will be? That will simply be 4, right? Okay, and I think I am speaking much ahead of my writing. Okay, so this is 2 times 2 because x equals 2, that is 4. And if I calculate my df dy, again, I'm just doing it mechanically, all right, not from the basic definition, that becomes 8y. So if I write my df dy at 2, 1, what will that be? That will be 8 times 1, that is 8, okay? All right, so here we go, 8. So let's quickly review a geometrical description of this. Now, before going further, let's quickly notice one thing, that the value of the function at 2, 1 is 2 plus 2 is square plus 4 times 2 is square, right? Okay. So, sorry, 4 times 1 is square, and that is going to be 10. So the level curve of the function through this point is, let's set that equal to 10. So we have x square plus 4y square equals 8, right? So this is going to be an ellipse, right? X square over 8 plus y square over 2 actually, y square over 2, and that equals 1. Or, I mean, if we want to write a little more formally in a known format, so we have x over 2 square root of 2 square here, and then in the next part we got simply square root of 2 square. Just to, we will sketch this level curve just to go and see these points much further. Okay, so I did this. I just brought a live script for you. Okay, I don't have to bring z in, but still I decided to. And our fxy is 2 plus x square plus 4 times y square. Okay, and we have also the level curve. And what was our level curve? Our level curve was this ellipse with this much as semi-major axis, this as the semi-minor axis. So we'll just take 2 square root of 2 cosine t equals x, and square root of 2 sine t as y as our parameterization. So what I'm going to do is this, that instead of watching me type the commands, which we have done many, many times, I'm going to complete writing these and bring it back to you. And you can always, in case you want to see what I wrote, you can always just pause and note it down. So I wrote everything in here. Excuse me. Hit Control Enter, and then we have a graph. So let's take the graph to the plotting window or in the figure window. So here, yeah, we have a graph in the figure window, and also we did this that we graphed the plane x equals 2 in here. Okay, so let me bring this back. All right, so this is the plane x equals 2, so x is like constant here. And why is it not rotating? Because I have to choose this. So this is the plane x equals 2. So when y is 1, remember we were looking at 2, 1. We are somewhere around here. And the slope is how much? The slope is 8, the value of the partial derivative. Okay, let's change the color of these because we don't really need to be that fancy, and I clicked on wrong thing here. So edit figure properties, and again, why don't I do this? If it takes too long, then that's what I'm going to do that in the background and then bring it back. But so here we got plotting. In the plotting, we'll just go with white. All right. Okay. So now here we are. So you can see here for corresponding to x equals 1, the slope at y is how much? Sorry, the slope at y is 8. Remember, that's what we got. And if we go ahead and plot the plane, say y equals 1, so let's do that. So here is our plane, y equals 1. Okay, so as x varies, then at 2, if you look at the slope, so here I brought the curve for you, and if you look at the slope of the tangent line here, you know, along the variation along axis of x in the plane y equals 1, that will turn out to be how much? 4, because we are at x equals 2, 1. So at the point 2, 1, okay, so we found the rate of change in the direction of the x-axis and the direction of the y-axis. Now let's say we want to find the rate of change in other directions. So say for example, I am taking this direction, 1, 1, or if I want to make a unit vector here, okay, so the unit vector here, if we divide it by the magnitude, 1 over square root of 2, 1 over square root of 2 will be unit vector in that direction. So what we need is that we need the rate of change of the function in case the movement in that direction. Like earlier we just did it according to going along the axis of x or the axis of y. All right. So we would like, so we had this function and we are talking at the point 2, 1, and what do we want is rate of change of f, okay, at 2, 1 along the unit vector. I mean, we wanted to go along 1, 1, but then we changed it to unit vector because that will be easy to work with. So along 1, 1, a unit vector is 1 over square root of 2, and here just happens to be that the y coordinate is the same. All right. So what will happen here? if you look at this, then since we are starting at 2, so say we move in the, you know, along this vector, then 2, say by a parameter value t, then what will happen? 2 will change by t times 1 over square root of 2, or simply t over square root of 2, right? And the y coordinate will do what? That will change from 1 to 1, and then by the same quantity, because this happens to be the same quantity, it will not always be that. So the derivative in this direction, let's call it, say, u hat. Okay, it's called the directional derivative. Okay, in the direction of u. Okay, so that derivative, we can call it df du. Okay, if we, sorry about that. Okay, that will be defined by this limit, if it exists, that t goes to 0, and what we have is now that we got, we will take the change in f, okay, in between these points, right? Sorry, change in f as we move from 1 to what? This value, change by t, and then divided by t. All right. So let's just quickly see what this limit will be. So, sorry, if you look at this, then what the value of this quantity is going to be, I'm just going to substitute in here all the values. So let's quickly do that. That substitution wouldn't take that long. So we got what we got, this for x, okay, and this for y, and we will let the machine do the algebra for us. So what is this whole thing? If we expand it, okay, that's how much this comes out to be. So this quantity here, or let's just take this one here, okay. So in here what we have is, this would be limit as t goes to 0, okay. This is the first one, okay. And what was f21? That was, if you substitute those values in there, remember that was a 10, right? So this becomes equal to, these cancel, right? Excuse me. And then we may treat, first of all, let me get rid of this here. Sorry about that. Okay, so here our answer will be plain and simple. How much? 6 square root of 2 after we take the limits, because t cancels out, and when t cancels out we simply get this quantity here, okay, equal to, so we got t, this t is out, so the answer is 6 square root of 2. Okay, now notice another thing here, that is, so this is the directional derivative in the direction of 1 or 1 over, and or if we write the unit vector, then it's 1 over root 2, 1 over root 2. Okay, now let's just get an easier way to obtain it, a procedure for that. So that will go like this. So remember this. Say I am looking at, say z is a differentiable function. Okay, let's just first assume that we are working with a differentiable function, and later we will deal with the examples to elaborate the exceptions. Okay, so let z be a differentiable function of x and y. All right, then in that case, for the directional derivative along, say we are taking a vector, we are calling say u hat. All right, and let's let that be, say, so let's let that be, say, u1 u2, and u1 u2, you know, are components of a unit vector, right? Okay, so and u1 u2 here are fixed. So what happens now, and we are computing it at, let's say we are computing it at any, you know, at a point, say AB, right? So what will happen is x will become a plus tu1, right? And y is going to become b plus tu2, okay? And then, so what we have here is, we have z as a function of x and y, or f is a function of x and y, where we got x as a function of t and y is also a function of t. So if I am taking df by dt, and actually, you know, instead of df du, you could write that as df dt, because t is the variable in that direction. Then by chain rule, what do you get? df dx dx dt, right? And then plus df dy dt. And who are dx dt and dy dt? So dx dt is u1 and dy dt is u2, right? So you get simply this, u1 times the derivative with respect to x, and u2 times the derivative with respect to y. So in this case, for example, remember this, say we wanted df dt in this direction. What we could have had is this, that if you remember that we have, what do we have? 2, 1 as df dx and df dy. Let me just write it as like this. 2 was df dx, and a is how much? 1 over square root of 2, right? Then plus, remember what was the derivative with respect to, no, that was a 4, I'm forgetting. That was a 4. And then 8 was the derivative in the direction of y, right, at the point 2, 1. So we get 12 over square root of 2, which actually comes out to be how much? 6 square root of 2, right? So in other words, if I'm looking for the directional derivative along this, right? then, and of course, this is computed at A and this is computed at B because we are looking at AB, right? So if I'm looking at the directional derivative along this vector u1, u2, then that is simply this quantity. And if you want, you can do this, excuse me, and you can write that as a dot product, okay, as a dot product of, for one component, take these vectors, okay, that is, let me put a comma here, and then dot, all right. So we would write a dot here, excuse me, dot this vector, right? So that will be an easy, you know, working method for obtaining directional derivative.